Hi, welcome to MEN 368. We were talking about Castigliano's theorem. So let me write it down. Castigliano's theorem. So just a quick recap. It's used for finding displacements at specific locations in a beam. This is our most common use. By the way, it is not just restricted to displacements. You can also find rotations or what is called slope, etc. Okay, so how does it work? So the way it works is, if you have a need for finding the displacement at x equal to xi, find the complementary energy in terms of force at x equal to xi. B, differentiate the complementary energy with respect to force. This will give you the displacement. That's how it works. So you got to do two things. You got to find the complementary energy, and then you have to differentiate the complementary energy with respect to the force. So what does a complementary energy mean? Meaning is this. If I draw force versus displacement, this is the stored energy. This is the complementary energy. Mathematically, this is called a Legendre transform. You don't have to know that. All you have to know is it is this thing. Okay. So let's see, how do we find this for a specific problem? So we are now going to look at a new problem. So our idea is, our basic, most important result is that the total complementary energy of a beam, the symbol I am using is G, equals integral 0 to length of the beam of f squared over 2 EA plus v squared over 2 GA plus m squared over 2 EI plus t squared over 2 GJ. This is over the length of the beam, and I have written ds because it works even for curved beams. It does not have to be straight. It can be any beam. So ds, or you can write it as dx if you like. So that's how it works. Okay. So this is axial energy, axial complementary energy. This is shear complementary energy. This is bending complementary energy. This is torsional complementary energy. Just to get you an idea, these two things will contribute less than 1%. Unless the beam is really large, I mean really short. So for short beams, this will dominate. For long beams, this will dominate. Okay. So now let's look at an example. So up to now, I looked at a cantilever beam and you're thinking, what's a big whoops? You know, cantilever beam, I already know this, delta equal to FL cubed over 3EI, and after a lot of difficulty, you found it. Who cares? Fair enough. Let's look at something that's quite different. Okay. This is an actual design problem. You are going to design let us say a crank, like a what is that? A crank by which you can open the lug nuts in your car. You know what I'm talking about, right? So here's your car. Here are all the lug nuts, and you have this little L-shaped device that you go in and you're going to apply a force here. Okay, and we have to design this. So imagine what's happening. So for all practical purposes, when I connect the lug nut when I connect my wrench to the lug nut, for all practical purposes, it's a fixed beam. I mean, that end is fixed, you know, until it starts moving. Once it starts moving, you don't need much force. So your design is before the thing starts moving. Before the thing starts moving, for all practical purposes, it's a bar that's sticking out of a wall like that. Right? The wall represents the tire and this bar is my lug nut. Okay? And I'm going to apply some force on this, F. And the question is, how big should this thing be? Should it be 3 mm dia, 4 mm dia? What should it be? 3 centimeters, 10 centimeters, what? Right? So the decision is based on stiffness. I got to figure out, if I apply that much force, how much will it deflect? You know, think of like making it this out of rubber, right? What will happen is, as soon as you apply the smallest force, it will bend, it will distort, and that's the end of it. It will not actually deform. I mean, it will not actually move the nut. You will not be able to apply a torque to the nut. Okay. So what happens is, I apply a force. Now this is a bent beam. So this is actually an example of a force on a bent beam. And our simplest problem is like this. I have a beam that's bent like that, L1, L2, and I'm applying a force which is into the page, and this end is fixed. It makes sense to you? The question is, how much will this deflect? Now, if you do it by conventional methods, this is very hard problem, because you have a bent beam and you have sharp cross sections and this, that and the other. But the beauty is, I am going to do this by using the method of Castigiano. So what I am going to do is, step A, label straight sections of the beam. So this is, I'm going to call this AB and BC, right? And before we proceed, I want you to remember that ultimately what I'm interested in is, Castigiano says, I need DG, DF, which, because of only bending and torsional energies, that will look like 0 to L, M, dm, df over EI plus T, dt, df over EI, dx. Okay. So, I label the straight sections of the beam, B. Mark X variable along the beam. So X is not the X coordinate now. It is the variable that tells you where you are on the beam. So that's why I wanted, so sometimes people will call it the S variable rather than the X variable, because ds is arc length. That's really what we are doing, okay. So this is arc length. So I'm going to call this the S variable from now on. So please remember, this is the arc length. So I'm going to, and where do I start? Starting from free end. Please remember, this will make your life a lot easier. Start from the free end, then you don't even have to find the reaction forces. Okay, so that's a very important point. So start from the free end, and if you start from the free end, you don't have to find the reaction forces. It's very easy for you to do the next steps. If you want, you can even flip the picture over if you feel that that's better for you for the free end. The picture actually does not matter. Whether it goes from left to right or right to left, who cares? Okay, so just to make life easier for us, I am going to flip the picture over. So the picture looks like this. You know, again, it's one of those things where it's prejudice against left-handers. You know, we don't like things that go from right to left. We only want things that go from left to right, right? But I am a left-hander, so, you know, so I always feel this, but it doesn't matter. Or if you feel more comfortable with that, do that. Now I'm going to mark the coordinate. So my x coordinate goes like this. So this is L1. So this is x equal to L1. And I'm also going to call it S. So let us keep with that. Okay, sorry, I will not call it X. I'll call it the S coordinate. S equal to L1, sorry, L2, and then S equal to L1 plus L2. Okay, and in each section, find the bending moment and shear force, sorry, and torque as a function of S. Okay, so this was my point C, this is B, that's A. Okay, along the curve BC, I know that S is going from 0 to L2. Okay, how much is M? Bending moment, that's easy, right? I have a force that is pointing down into the page. This length is S, so I know that my bending moment is F times S. So F is the force. Okay, what about the torque due to this force? Students have a lot of trouble with actually figuring out which portions have torque and which portions of the beam don't have torque. Okay, so I am going to spend a little bit of time in an aside to talk to you about figuring out what happens in bent beams and what happens to torque. So let us put, so I have a beam. It's like this, right? I'm going to draw this in 3D so you can see what I'm talking about. So here is some portion of a beam, okay? And there's a force acting somewhere else. Okay, the beam itself may be like this and like that, we don't really care, but there's a force acting somewhere else. The question is, how much torque is there on the red portion? What the heck is the red portion? The red portion is this portion, that portion. Answer: torque will be equal to perpendicular distance between beam and force, which means it is this distance, Perpendicular distance means the shortest distance between the point of application of the force and the beam. So it is not that one. You have to find the closest distance. Okay, that's the perpendicular distance times the force perpendicular to both of them. Now, this is really bizarre, but that's what you have to do. So, there are two conditions that have to be satisfied for there to be a torque on a shaft. The first condition is that the force should not go through the shaft. Notice that unless the perpendicular distance is not zero, there will be no torque. The second thing is the force should be perpendicular to the axis of the shaft. So not only should it be perpendicular to the shaft, there should be a distance. Also, the force should be perpendicular to the shaft. Then and only then will there be a torque on the on the shaft. For example, let's say I'm looking in the plane 2D xy, and here is the shaft, and a force is acting here, F. Will this have a torque or will it not? Well, the force is perpendicular to the shaft, so that is good. But the problem is the force is going right through the shaft. The perpendicular distance between the force and the shaft is 0. The distance of closest approach of the line of action and the shaft is 0. So that means there will be no torque. Okay, this is true even if the shaft is here and the force is there. Notice, if I extend the force and if I extend the shaft, if they intersect, there will be no torque. They have to not intersect and the force has to be perpendicular. Only the perpendicular component will actually matter. That's how you determine the torque. For bending moment, it's simpler. Either the force is perpendicular or there is a gap. What do I mean? Let's look at this situation. Force F. Well, if I extend it, this means bending moment present, torque absent. Can you see that? No torque, only bending moment. How about this? Bending moment present because it's going to turn it like that. So if I draw a line like that, it's going to turn it like that. Torque is absent. Why is the torque absent? Notice that the force is parallel to the shaft. So no torque. Okay. Suppose it's like this. And you have a force that comes down there, pointing down like that into the board. Then bending moment will be present because the force is perpendicular to the shaft. Torque is present because it satisfies both the conditions. Force is perpendicular and the distance of closest approach is not 0. Right? So you have to know what will happen. How will I get a pure torque and no bending moment? It's actually quite easy to get pure bending moment and no torque. To get pure torque and no bending moment, you have to do something else, which is you have to apply equal and opposite forces. So if I do one force like this, another force like that, then each force will have a bending moment, but they are opposite effects. So you will not get any bending moment, you will get only a torque. This is what happens. So in this case, moment not present, torque present. This is actually what happens in a fan. You remember we did the fan problem? In that, what happened was, there was only torque, no bending moment. So I wanted to understand that for torque to be present, there has to be the minimum, the closest approach between the force and the extension of the shaft must be non-zero, and the force has to be perpendicular to the shaft. Both the conditions have to be satisfied for torque. For bending moment, either the force is perpendicular to the shaft, or there has to be a set gap distance. Okay, that's how it works. So now let's get back to our problem. So M is F times S. Torque is 0. Why is the torque 0? Because the force, there is no gap distance. Yes, the force is perpendicular to the shaft, but there is no gap distance, so the torque is 0. So I will also calculate dm df, which is just S. dt df is 0. Okay, so that's that portion. How about the next one? S equal to L2 to L1. Sorry, L1 plus L2. On this portion, is it obvious to you that bending moment will be present because the force is perpendicular to this shaft? Torque will be present because the force is perpendicular and the minimum gap distance is L2. So both of them are present. To compute the bending moment is easy. It is a force times whatever is the distance. So this is F times S minus L2. Because S equal to L2, there is no bending moment. As it grows, the bending moment grows. Okay. So that's that. Torque is force times distance, that is F L2. dm df is S minus L2. dt df is L2. So creating this matrix is the crux of the matter, this table, because now I can do the integral. So my displacement will be integral 0 to L L2 of M dm df over EI ds plus integral L2 to L1 plus L2 M dm df over EI plus T dt df over EI ds. So let us see if we can do these integrals and then you will get the answer. So let us see. How come there is no dt ds here? Remember, that's why there is nothing there. Okay, so remember that. Okay, so now let's calculate it. Delta equals integral 0 to L2 M is Fs, dm df is S, so that's S squared over EI ds plus integral L2 to L1 plus L2 M is F times S minus L2 dm df is S minus L2 over EI ds plus integral L2 to L1 plus L2 T is FL2, dt df is L2, so FL2 squared over EI ds. So each of this is M, this is dm df, this is T dt df. So let's do the integral. The first one gives you a very simple result. This will be F L2 cubed over EI plus the second one will give you a very similar result. If you do the integral, and I will let you do the integral, you will get F L1 cubed over 3 EI plus the last one is a very simple integral that will give you F L2 squared L1 over GJ. Thank you. Notice the three pieces. Okay, let's see what the three pieces mean. Remember, my shaft looks like this, right? So FL2 cubed over 3A is because of the bending of this shaft. Think of this as a fixed support and it bends. FL1 cubed over 3A is because this shaft bends. Right? So it will bend down. So think of it this way. This shaft which is coming towards you is bending down like that. This shaft which is sideways from you is bending down like that. So the two displacements add up. And the last one is because this shaft is rotating like that downwards. Right? So this is bending, rotation. Notice that your most important and probably the most difficult aspect of this is making sure you know how to compute M and T for different sections and calculating these two. The integration itself is pretty routine. Yeah, it may be tedious, but it's not challenging. Calculating M and T are the real crux of this matter. Okay, that's why we start teaching you about shear forces and bending moments since mean 221. Because we need you to have a lot of experience with it, because Castigiano's theorem, everything works on this. So your real test is your ability to find shear forces and bending moments along shafts. If you can do that and write functions for it, you can actually find all of these things, displacements and everything in a very simple way. Thank you.